Good morning. So, we all know that writing performant code is hard, and I presume since we're all Ruby developers here, we know that writing performant Ruby code that does a lot of stuff is really hard. So there's this application that I work on. It's called CocoaPods, and it got to be pretty slow at scale. I'm sorry, I contractually have to say those words. And this is going to be the story about how my team made CocoaPods bearable and usable again. So I'm at SE Giddins everywhere on the internet. You might have seen my name before on GitHub or Twitter or my face. About a year and a half ago, I joined the mobile developer experience team at Square, where it's my job to keep all of our iOS developers happy and productive, or as happy and productive as, a bunch of developers can be. You might also have seen my name in connection with a pair of projects called Bundler and Ruby Gems. I've commented on quite a few issues and pull requests in the past. I've even obsessed a bit about performance in those projects, but I'm not really here to talk about them today. So, quick aside, how many of you write Ruby almost every day? Well, now I can see who's paying attention. And then how many of you write Ruby that's deployed to a web server? Oh, pretty much everyone. So I actually do neither of those things, which makes me a bit of a stranger speaking at a Ruby conference. But I hope in return I have some extra perspective on what other ecosystems have to offer their developers. Okay, so what is this CocoaPods thing, and why are we talking about it here at a Ruby conference? Sam, you said you work on iOS stuff. Well, I do both. So CocoaPods is a rather large command line tool, and it's all built in Ruby, and it got to be slow at scale. And every time you would run the pod install command, which is sort of the main way you use this tool, it would take like 3 minutes on a brand new, 2018 top-of-the-line MacBook Pro, and that was terrible. So it was time to sort of dive in and help boost my team's productivity. So with the help of some amazing tools, some patience, and a very, very vague recollection of how big O notation works, we managed to cut pod install times in half. By changing less than 200 lines of code, we saved 90 seconds per install, and all via a set of performance improvements that are applicable to basically any Ruby library. So CocoaPods is kind of Ruby Gems and Bundler put together, but for iOS. So it contains a definition of libraries, these things called pod specs, with a way to integrate them into a user's application, a pod file. And if these names look a little bit familiar, it's not a coincidence. So it turns out that CocoaPods was written to be as much like Bundler and Ruby Gems as possible, for better or for worse. But there is a little difference here. I'm not sure if you can spot it in this chart. It's kind of small, but that little difference is my friend, my enemy, the application that keeps me warm during the winter because no matter how new a machine I have, it always heats up. Xcode. So I'm gathering from the laughter. Some of you may have used Xcode before. For those of you who haven't, or for those of you lucky enough to have forgotten, it's Apple's proprietary toolchain for compiling apps and libraries. It uses its own manifest file format, which dates back to the early 1990s. Woohoo, P-lists, said nobody ever. And it invokes many, many compilation tools like Clang and Swift-C and the bunch of esoteric ones that Apple has written and that crash like 1 out of every 50 times non-deterministically. I have statistics on this, I promise. So in a way, CocoaPods has to do a lot more than RubyGems or Bundler does, because it has to integrate with this opaque and monolithic third-party thing. You know, RubyGems and Bundler, they're just kind of like, well, we're gonna make some network calls and download some things and put them on the file system, and then we're gonna set up some global variables, and we're done. So going through what happens when you run this pod install command, it'll go and, you know, update the set of spec repositories, you know, downloading manifests. It'll go through dependency resolution. It'll then go and download those actual dependencies. It will install those dependencies. It will generate an Xcode project. It will integrate that Xcode project into your own Xcode project. And then you're done. So it exists. You say it was slow. So what? Why did I bother spending time working on CocoaPods performance? So one of the interesting things about doing performance work in software is that performance generally doesn't get better without effort. In fact, if you don't do something, performance usually gets worse because you're doing more and more stuff. You know, you have more users, more objects in the database, stuff like that. You typically don't accidentally fix performance problems over time, so you need to sort of keep on chipping away at them to keep things steady in the face of growth in whatever it is your application does. Okay, but optimization is fun for some certain definition of fun. Being able to iterate rapidly, to run a tool over and over and over, means that it's less frustrating to go into work every day and, you know, sit down and be like, I'm ready to write some code, and then your computer says back at you, no, you're not, wait 5 minutes. And then you go get coffee, and that turns into 15 minutes, and you come back and you forgot what you were doing, so then you run git pull, and then you have a merge conflict and repeat until the end of the day. And then there's this buzzword that we really like to throw around, scale. What that means is sort of stuff growing tends to be valuable, so being able to grow stuff means that the thing you're doing might be worth more money someday, just in the abstract. And finally, free performance is hard to find, as I was talking about earlier. So raise your hand if you've ever asked yourself this question: I have a slow Ruby app, what am I going to do to make it faster? Yeah, a couple of you. So there are actually a couple of questions you should ask yourself when you start thinking, how do I make it faster? And step one is it actually slow? What is the app doing? How often does it do the thing that's slow? If something takes like a couple of hours, but you run it once a year, is it really worth making it faster? Again, would it being faster make a difference? You know, would someone pay money for it to be faster? And instead of worrying about making the application's performance faster, can you make it do less work? And finally, how can I keep the problem that I have, that may or may not be a problem, from getting even worse? So to answer that question of, is my app really slow? You can answer like, how much money would I invest to make it 10% faster, or 50% faster, or 90% faster? How do I know which part of what it's doing is slow? Most applications do a lot of things. You know, even your most basic web application, well, it's going to like process a request, and then go to the database, and then render a view, and then send that back out over the network. There are a lot of steps going on, and that's in the most simple case. So there's sort of this scale of precision to answering that question. Step one is the like, well, something happened and I've gone to Twitter. So I'm like, this is terrible, this is slow. A lot of people, it turns out, just stop there because they actually don't care any more than to vent off some steam. And then you can start to actually put some numbers to that and say, this took 10 seconds, like running this thing took 10 seconds. And you can zoom in a little bit more and say, this part of the pipeline took 10 seconds. And finally, you can go, all professional and be like, well, this method was called exactly 97,645 times, averaging 23 milliseconds per call, taking up 48% of the application's total runtime. And I guarantee you, if you have an answer like that, your manager will listen to whatever you say after that. You'll be able to do whatever you want for the next week. So this brings us to profiling, and I came up with my own definition of profiling, which is that it's sort of the art of putting numbers to the feeling of this feels slow. It's going from that, like, I want to rant on Twitter to I actually want to fix the problem. So, okay, great, profiling. I should probably do that because Sam's talking about it and it's on a slide. So what can I profile? Easy things, or you can profile method calls. You can sample call stacks. You can look at memory allocations. You can measure disk I/O, measure network I/O, database queries, garbage collection. Turns out you can profile pretty much anything. And so my work on CocoaPods, specifically some of the work I did last year, focused on method call profiling and call stack sampling. But I've actually done a lot of performance work, it's been a balance of measuring and improving all of these different things. Quick aside, one of our other core contributors got some really amazing gains on their project by profiling allocations and memorizing things like implementations of the hash method and joining up path names. We'll talk a little bit about the power of memorization later. So, profilers, and they're the tools that we use to do profiling. And just like most tools, it's important to pick the right one for the job at hand. So, sort of the simplest type of profiler is what's called a tracing profiler. And what that'll do is it'll basically instrument your application, and every time something gets called, it'll increment a counter and it'll run a timer. That's, a pretty simple thing to do. But there are some problems with using tracing profilers. One of them is they can distort relative numbers. So if you have really, really deep call stacks, the overhead of the tracing will get added into things higher and higher up the call stack. So if all you're doing is performing a bunch of addition of integers, hooking that method is actually going to take longer than adding the two numbers. Going along with that distortion is tracing profilers can just make running a program really painfully slow. So once someone came onto our issue tracker and was like, well, CocoaPods is slow, and we were like, well, why don't you try profiling it and telling us what is slow? And we got back this gem of a response, which was like, well, if it takes 35 minutes to do it without profiling, it's probably never going to finish if you run it under a profiler like RubyProf. Sorry about that. I really hope you didn't just spin that up and run overnight in the middle of the summer. So there are also profilers like allocation profilers. So this is a specific type of tracing profiler that will count memory allocations instead of method calls. Maybe it'll even say how much memory is being allocated and how much is being deallocated. There's been a lot of work on Ruby with its memory footprint over the past couple of years. And if you wanted to work on that and see the effects of like symbol garbage collection and all that, you could look here. So they suffer from similar problems as method tracing profilers, but they're even worse because I don't know if you know this, but a typical Ruby program it allocates and deallocates a lot of objects because guess what? In Ruby, everything's an object. So everything you do has an allocation in it. So then we get on to some of the fancier things you can do, such as using a sampling profiler. So I love sampling profilers because they let you look at what your program is doing, but from the outside. So they generally won't interfere at all with the normal execution of your application. The downside of this, of course, is that it's possible to miss things. If you're only sampling, let's say, 100 times a second or 1,000 times a second, you can miss things. And it's luck whether or not you'll capture any particular stack trace. It's whether your program gets paused and sampled at exactly the right time. So as a result of that, you can't tell like exactly how many times something has been called, or whether even a really, really fast method has been called at all. You just sort of get an answer to the question of like, well, what were the stack traces when you paused the program and looked at them? And what you typically look at is, well, what's at the top of the stack at that time? But it turns out sometimes you don't need a fancy tool that someone with like a PhD has thrown together for their thesis. And oftentimes, like, trying to interpret the output of a profiler is, I don't know, it's just really hard. It's looking at a bunch of numbers and trying to make sense of them. And the best GUI that we have available is like a 1990s era, sort of Linux-y looking desktop app. And so I got to the point where I was like, I'm not having fun looking at these stack traces anymore. Loading up like 40 megabyte text files in Vim is not really my thing. So I decided to go really, really simple and do things like, well, I'm calling this method. I know I'm calling this method. I want to see how long it takes. So I'm going to write some code that says, measure how long it takes to run the code in this method. And it really helped me focus on what I already knew was slow, because I've spent a lot of time in the CocoaPods code base. I have a good idea of what's fast and what's slow, where the particular problems were. Also, I looked at the console output, and I was like, it's taking a really long time to get to the next, print statement. So I wonder what's going on in between here. Oh, it's one method call. Well, that one's the slow one. It's also much more likely to tell you something about the distribution of how fast or slow different calls to a method are. Let's say you call a memoized method. So the first time you call it, it can take a really long time, but every time after, it's almost instantaneous. Well, at that point, you want to know that there's these two different access patterns. You don't just want to see an average or see the maximum or the minimum. So me being me, I built a tool to automate the thing that I just said I didn't want to automate. But it turns out I just didn't want other people to automate it for me. So I wrote this gem. It's open source. It's on GitHub and Ruby gems and stuff called Chronometer. And it automates this low fidelity tracing. So it's really simple. It wraps methods by redefining them, and it times how long they takes and records things like their parameters and the return value along with the duration. And it can output results in a format compatible with Chrome's really cool tracing view. I don't know if you've seen that, but it's used by Chrome developers to figure out like how long a web page takes to load and where all that time is going. And yes, it's all going to your fancy JavaScript. And it's a tool that does all its work in process. So you can just write code that uses those timing results. If, let's say, you're interested in gathering metrics or something like that. You may have noticed the pattern earlier where it was like, we really like things that were like gem files and pod files. So you'll never guess what Chronometer has support for. A chrono file. So I wrote a really silly little DSL that lets you sort of just say, hey, measure this class and measure its methods, and being able to provide some other things like context and like the ability to evaluate random pieces of code to attach to that method. So yeah, using in practical terms, my profiling work meant using a mix of RubyProf, which is a tracing profiler. It's really cool. It's kind of like the standard Ruby profiling tool. RBSpy, which is a sampling profiler that Joy Evans wrote on Recurse Center Retreat, which is also super cool. And Chronometer, which is a thing that I wrote and that by no means any of you should use. But in all seriousness, all three of them are really great, and I used all of them extensively. But they were each useful for answering different sets of questions. At the end of the day, Chronometer sort of hit the sweet spot for the type of software that I was developing, because I knew where the problems were and I was interested in measuring, and I work in a company and I have to justify the work that I do, so I really like gathering numbers. And so, as I was talking about earlier, like Chronometer runs in process, so I wrote a little plugin for CocoaPods that takes those timing results and sends them off to a logging server. So now I can go online and make graphs and be like, yes, all these different parts of installation are taking exactly this long for this particular person on this week. This is like aggregating different durations on CI over the past year of some of the different phases of installation. But I can make these graphs whenever I want. Whenever I want to go and work on CocoaPods performance, I'll find some graph that justifies me spending a week or two on it. I also got these Chrome trace files, and not really a great example here, but like you can see for each method invocation what all of the arguments were. So that's been really cool for trying to figure out, like, is this same method being called 10,000 times on the same object with the same exact parameters? And if so, I probably shouldn't do that. So profiling and a lot of digging into the code revealed some fundamental problems with CocoaPods architecture. And it also showed a bunch of smaller things that were a lot easier to optimize. Things like don't do something in a loop if you can do it outside the loop. So the first big problem with CocoaPods is it's basically a giant graph traversal problem. So it's kind of the bottleneck that all build systems end up fighting. So what is graph traversal? It's taking a graph and walking through it. So you have something like A which points to B and A which points to C, and both B and C point to D. So you can reach D from A, but that's really simple. This is the dependency graph for Square's networking library, and this is just the networking library. There's lots of code that sits on top of this. So as you can imagine, writing code to walk this graph that isn't as optimal as possible meant that CocoaPods got really slow. So sort of the base problem you do in build systems is you say, how do I find all of the nodes that come after this one? So it's really tempting to say this is a problem for recursion. A is followed by B and C, so let's figure out what B and C are followed by and recurse. But then you end up in that small example visiting the D node twice. And you say, oh, not a big deal. Well, that's 2 times as much work. But imagine 50 more things come after D. And then you repeat this problem for each one of them. And it's not just CocoaPods that has this issue of sort of doing the naive graph traversal thing. About 6 months ago, my Android counterparts were looking into an issue where merging resources in the Android Gradle plugin took like an hour, and it used to take no time at all. And they found out it was doing naive graph traversal, and they went in and they patched it, and their compile times went from like 2 hours to 15 minutes. So why does this happen all over build tools? Well, there are lots of DAGs, directed acyclic graphs, and they describe dependency structure. This is the same type of thing that like Bundler and RubyGems use when looking at your set of dependencies in your gem file and doing dependency resolution and all that. So every node has a list of dependencies, and there's just one rule, which is you can't depend on something that depends on you. And most operations rely on a fancy property called the transitive closure of a node, which is what are all the things that I can reach from this node, no matter how many steps it takes me to get there. So there's this library that powers dependency resolution in Chef and Bundler and CocoaPods and RubyGems called Molineo. And it had a method to go and sort of do the same thing, figure out, well, kind of the opposite, figure out all of the nodes that point into this one. And it did the naive thing. It was like, well, everything that points into me, let's do this recursively. And that was really slow. And so the way we changed that was to sort of track all the set of nodes that we'd visited. And something that was, sort of exponentially exploding in how long it took became constrained to the size of the graph. So something that goes along with trying to solve a lot of graph traversal problems is memorization. So let's remind ourselves of the simple dependency graph. And then let's say that some build setting for the target A depends on a build setting for the target of B and C and D. And yes, this is how build systems work. It's kind of terrifying. And if you implement things the naive way, they can get slow. They can get really slow. Like really, really slow. Like imagine for each one of those things you have to look at some file on disk and compute a property of it. Maybe you have to open it up and run a Mach-O parser and determine whether something is a valid Mach-O binary or not, which is a thing CocoaPods does. And then recomputing these build settings for B and C and D get really, really expensive. So the idea behind fixing this is memorization, where you compute something once and then you store the result. So this is slightly different from caching because, well, we all know one of the three big problems in computer science is cache invalidation. But when you memorize something, there's no invalidation that can happen. We're just lazily computing a value and storing it. And the next time it's needed, we just go, aha, we stored this, and we return that instead of recomputing it. And it turns out we do this a lot in Ruby. You know, if you've ever seen something like this pattern, you have some expensive to calculate method, and you say, oh, I'll just store it in an IVAR and use or equals. This is memorization, a fancy word for a really simple concept, just like a lot of computer science. So this works really great. But there are some pitfalls. Like, imagine that the return value for that expensive to calculate method can be nil or false. Then using or equals won't kick in the short circuiting, and you'll end up recalculating nil or false over and over again. And this is not ideal. So instead, we turn to something a little bit more complicated. So we check and see explicitly, like, is this something that we have set before? If so, return it. If not, calculate it. But even this approach has issues. Like, what if we want to be able to reset the memoized value? Once we've stored that instance variable, something's stored in there. There's no going back from that. This can also get a bit weird when you start subclassing, as where in your method you call super can start to make a really big difference in behavior. So, of course, I did the me thing, and I wrote a little DSL to be able to define build settings that are memoized, and also added a bunch of helper methods, because I really like helper methods. Things like, oh, hey, this thing returns an array, like take all the nils out, or unique it, or sort it, or freeze the value. So my little helper, what it does is it uses a hash stored into an instance variable, and it calls fetch on that hash. And what fetch lets you do is it lets you basically detect whether or not a nil you're getting back is because nil was stored in the hash, or because nil is just the default value when a key is missing in a hash. One of the problems with not having types in Ruby. I know other people have talked about that. So one of the benefits of using this approach versus the simple or equals approach is that you can easily clear all of that state by just discarding that one instance variable, instead of needing to keep track of every piece of state that you're storing. And if we're smart and we select the key into that hash well, we're able to memorize multiple steps of a process. Like, for instance, what value the superclass would have returned and what value the subclass would have returned. So this DSL and a quote-unquote big refactor I did allowed me to fix years-old bugs in build settings generation. Bugs that I tried to fix under the old approach, and it slowed down installation to be more than 5 or 10 minutes with the old implementation. So I came out of this with CocoaPods being a bunch faster, but also, it turns out, learning a bunch about software design. So CocoaPods isn't as fast as I'd like. As fast as I'd like would be defined as takes no time at all, so it'll never be as fast as I'd like. But even being more realistic, it won't be as fast as something like, let's say, a Cargo or a Bazel. Some of this, unfortunately, and to be honest, does come down to language. At the end of the day, Ruby is slower than compiled languages like, Java or Rust. Some of this comes down to the fact that what CocoaPods does is super, super complicated. iOS build systems and Xcode in particular have so many edge cases, and it's like just impossible to wrap your head around what expected behavior is supposed to be. And a bunch of this is also our own fault for having a system design that's 7 years old and it wasn't built to scale as far as Square has tried to take it. And, you know, a lot changes in 7 years, as I'm sure anyone who's inherited an old code base can attest to. You know, if you want to look at an extreme example for that, try and run Ruby from 24 years ago. So there are some particular design, you know, lessons learned. Exposing mutable objects was a terrible decision. It makes memorization really hard. It means that you have to have separate objects to hold computed values only when it's safe to do so. So things like after you're done assigning all of the properties. Unless you want to get cache invalidation bugs, in which case it's totally cool. Try and cache things wherever and whenever. You'll just get the wrong result approximately all of the time. We read and write to the file system everywhere, sort of inline, which makes it really hard to parallelize I/O. Versus, let's say, creating an in-memory representation of what the world should look like after running the command and flushing it all out to disk at the end. We also really value like really good and consistent CLI output, which again makes parallelization hard. So it means you have to figure out answers to questions like, how do I show progress, or what the underlying command invocations are, or, you know, failures that happen. We have really, really inefficient data structures, like our pod file and pod spec are stored under the hood just as hashes, you know, because the whole idea is, well, it can be serialized to and from JSON, and we'll make that the canonical representation. But it means that accessing any attribute means going through a hash. The entire Xcode project model is something we can thank Apple for, but it's a horrible object graph model that's really, really complicated, and our re-implementation of it is buggy. And because everything is built using nested hashes, it makes change tracking really hard, which is compounded by the fact that Ruby doesn't have any sort of copy on write data structures. So you either try and make things immutable and then have to make them mutable because like we're writing programs that change things, or you have to do your own change tracking. We also use eval on objects stored on disk. So our DSLs are just Ruby rather than pure configuration languages like JSON or YAML. And what this means is state can leak into the sort of pure representation of those objects, which means that it's really hard to compute stable hashes because there are multiple valid representations to compute them from. So things like trying to skip out on doing work you don't need to do is hard. We also just don't store all the information that we'd need to determine when something has changed. All that information just isn't present in what people check in to get. There also, up until a couple months ago, was an all or nothing installation operation. So every time you ran pod install, it would go and like recompute everything, even when nothing had changed. So you had to redo everything all the time, meaning that every invocation took the full minute and 30 seconds. Fortunately, one of my coworkers went and fixed this and implemented incremental installations, which has been super awesome. Now every time I run pod install, it's like 20 to 30 seconds, which is a lot better than a minute and a half. No time even to get coffee. The path name API in Ruby is like really nice. Lets you represent paths. I'm not going to get into it, but my answer to it is just nope. At the end of the day, the lesson learned was that the architecture of the app we were building mattered just as much as fancy algorithms or fancy tools. Picking your programming language is a trade-off, surprise, but we also dug ourselves into a corner with the Ruby code that we wrote. It's not just Ruby's fault that we have these problems. And so what's the future of this? Well, Square still is investing heavily in CocoaPods because we use it a lot, and we believe in it and the way it works. And the focus for us now is on scale. We've been making progress recently. We started with the build settings refactor that inspired this talk up through the incremental installation project that I said my coworker completed a couple of months ago. And we're not done yet. The future of good performance in CocoaPods is largely about changing design and adding new features that allow us to get away from hard problems wherever we can. So, thank you.
Okay, thank you, Samuel, for the talk. Any questions that you'd like to ask? Please raise your hands. Okay, no one? All right, let's give Samuel a big hand again.